So here we have the region W is the cone shown below.
Mm-hmm.
The angle at the vertex is 2 pi over 3, and the top is flat with height 6 over square root of 3.
Yeah.
Write the limits of integration over the region W dv in the following coordinates. Do not reduce the domain of integration by taking advantage of symmetry. So it looks like they want us to have a volume in terms of dz, dy, and dx.
Mm-hmm.
Okay? So let's see. If we go A to B, and then we go C to D, and then we go E to F, let's think about this in Cartesian. Okay, so first of all, I think that the Z is the easiest because the Z is just going to be from the bottom to the top, right?
Mm-hmm.
Okay, so that's relatively straightforward. So that's just going to be Z equals 0, Z equals square root, sorry, not square root, but 6 over square root of 3.
6 over.
Okay, just like that. Because you know what? If I did Z equals 0 to Z equals 6 over square root of 3, it would be a cylinder. It would not be a cone. So the thing is that the top bound is indeed Z equals 6 square root of 3, because it's flat.
Mm-hmm.
But you see that the height here varies with both x and y. So we'll come back to that in a second. But E equals Z as a function of x and y. So we'll come back to that in a second, okay?
Mm-hmm.
All right. Next thing is, remember the outermost integral. So if we're going to do dz, dy, dx, the outermost integral has to be a constant.
Yes.
Now, if we consider this as a projection onto the xy plane, we kind of talked about this in the last session, but it's definitely worth going through again. So consider the projection onto the xy plane. So if you're considering the projection onto the xy plane, then the way I like to think about it is you could imagine you've got like a flashlight here, and what would the shadow of this thing look like on the xy plane?
A circle.
Yeah, 100%. Now, we have to think about what the radius is going to be. I mean, consider this is a cone, and we know this goes out 2 pi over 3. You can imagine there's essentially a right triangle here, right? So this is like a right triangle.
So one thing I realized that I do need to clarify is that when the problem states that the angle at the vertex is 2 pi over 3, that's confusing for the sake of this problem. The angle at the vertex is actually from the left-hand side of the cone to the right-hand side of the cone, as viewed as the cone is given in the problem. So because it's 2 pi over 3, this entire angle, which would be 120 degrees, which makes a lot more physical sense because an angle of a triangle is only going to be obtuse, that is larger than 90 degrees, when we have one obtuse angle, but there's no way it can be a right triangle. So what that means is when we draw this side profile triangle, which you see here in green, which I have better pictured here in green. Now, this is definitely not to scale. And what I mean by that is this triangle looks a lot more isosceles to me, but the real triangle, which should be true for this problem, should be an angle of 60 degrees down in the lower spot, which is pi over 3, and then 30 degrees in the upper right spot. So when I was talking about 2 pi over 3 in this problem and pi over 3, I should have been saying pi over 3 and pi over 6. So the explanation is correct, but just change this angle in the part of the video about to come up to pi over 3 and this to pi over 6 as opposed to pi over 3, which are 60 degrees and 30 degrees. But the 30, 60, 90 special right triangle from geometry that we're about to see is still indeed correct. And This is why the maximum angle here that we rotate down to from the vertical z-axis here is indeed pi/3 radians when it comes to phi, which is the declination angle down from vertically straight up. So I hope that makes sense. Sorry for any confusion, but let's continue with our regularly scheduled program in the video.
So if this is 2 pi/3, then this is a right angle.
For phi.
So yeah, so 2 pi/3 in degrees would be like 60 degrees. So that means this is going to be pi/3. And then what that means is we know that this leg of the triangle is 6 divided by square root of 3. Because that just comes from the geometry here from this z. So if you recall, that's the shorter leg of the 30, 60, 90 right triangle. To go to the longer leg, to get from this point to this point, you multiply by the square root of 3. So when you multiply by the square root of 3, this is just 6. Okay, so hopefully you remember that. In a 30, 60, 90 triangle, to go from the short leg to the long leg, you multiply by the square root of 3. Okay, so that's a special ratio from geometry. To go from the short leg to the long leg, you multiply by the square root of 3.
Okay.
So but notice this is the 30-degree angle, the 6 square root of 3, right? This has to be 30 degrees right there. And then this has to be 60 degrees, because it's 2 pi/3. Okay. So anyway, that being said, this is 6. It actually should be 12 over square root of 3. Because to go from the short leg to the hypotenuse, you multiply by 2. Again, in the 30, 60, 90 right triangle. Once we have that worked out, we say, okay, we can figure out what x is, because this is a circle of radius 6. If we're going to integrate from -6 to 6 in terms of x, that's totally fine. This is going to be -6 to 6. Okay? But think about this. If you wanted to have y range from -6 to 6, that's not going to work because that would be a square. Again, if it seems too simple, it might be unless you think about it carefully. So we need to have y being a function of x. Now the reason we need y as a function of x is because this is a circle, right? At different x values, the height, y, is different, right? So that makes sense. Call a circle of radius 6 in good old college algebra or whatever, centered at the origin, would be x squared plus y squared equals 36. Does that sound familiar?
Yeah.
Because that's just r squared is 6 squared. We want to solve this for y, because we need y as a function of x. So that's y squared equals 36 minus x squared, and then y equals plus and minus the square root of 36 minus x squared. But notice, the positive part is the top part of the circle, because that's where y is positive. But then the negative part is the bottom part of the circle. That's because y is negative. So I'm thinking that in terms of y, these are the two bounds, the negative square root and the positive square root. So I'm hoping that's what they had here. Yes, that is what they had. So this is negative square root of 36 minus x squared. And then the top is square root of 36.
Working with a half a sphere, then my bound, it goes from 0 to square root of 36 minus x2, right?
Yes. So yes. So if you were just doing the top half here, it'd just be 0 to square root of 36 minus x squared. Yes.
Okay.
Yep, exactly. Okay. You okay with that? And then lastly, we got to really think about how we're going to do this z. Now, it's somewhat useful to know sort of the gallery. Certain surfaces you should be aware of. I mean, especially if you have to memorize these, I would definitely commit these to memory. So what I'm trying to say is there's nothing except for just knowledge of these. But notice they do look kind of similar to what's in college algebra. Because in college algebra, we had like x squared over a squared plus y squared over b squared equals 1 for an ellipse. But for an ellipsoid, we just add in the z. We've got these other ones. I'm thinking about that this is probably the elliptic cone. Do you see that?
Yep.
I'm thinking of, excuse me, it's probably the elliptic cone because the top could be an ellipse or the top could be a circle. In this case, the top is a circle. So what that means is A equals B, and they both equal 6. And the reason I know they both equal 6 is because when z equals 6 over square root of 3, then we get the equation, we get x squared plus y squared equals 36. Well, if you think about it, we actually can solve that for z, sort of. So let's explain how we might do that. If you divide everything by 36, we would have x squared over 36 plus y squared over 36 equals 1. But notice, usually it's equal to 0 over here, but what that means is at the top of the cone, we know that z equals 6 over square root of 3. We've already established that. What that also means is z squared over c squared has to equal 1. Now let's think about why that is. It's because if this is 1, so imagine this is like, say, minus 1 right there. You add it over, and then each of these has to be the same because, remember, the projection, which is like the footprint or the shadow on the xy plane, gives a circular cross-section. So since it's a circular cross-section, we know that A and B must be the same. It's not an ellipse, because remember, when the major axis and the minor axis are equal, the ellipse becomes a circle. And then they both have to be 36. In other words, A and B are both 6, thus A squared and B squared are both 36. So that means z squared over c squared has to be 1 at the top of the cone. So, that being said, we have to say, okay, z squared plus over c squared equals 1 at the top of the cone. But we can evaluate this because we know what z is at the top of the cone. So, z over square root of 3 squared over c squared equals 1. Well, that's just going to be, let's see, 36 over 3. And I'm just going to multiply the c squared over. So if I multiply the c squared over, we get that. And then 36 over 3 is just 12. And then you could square root that. So the square root of 12 is c. So let's see, c is the square root of 12, but the square root of 12 is square root of 4 times square root of 3. So this is 2 square root of 3. Okay? Because the only perfect square in 12 is 4. We know what the equation of our elliptic cone is. Our elliptic cone must be... Now think about this. Even though we found what c is always the same in this equation, and it's for any general x and y and z. So it's going to be x squared over 36 plus y squared over 36 minus z squared over, now c squared is 12, equals 0. So we should solve for z as a function of x and y. That's the goal, right? Because we already said that here for the bottom part, right? Okay, because we need the equation of just the surface. Okay, of the surface. I'm going to suggest let's multiply everything by 36 first. So that's going to be x squared plus y squared minus 3z squared equals 0, right? So when we move this over, it just becomes a plus, like that. I like having an electronic whiteboard. You can just do that quick. And then we got to take the square. We got to divide by 3, take a square root. So this is 1/3 x squared plus y squared equals z squared, and then take the square root. So we take the square root. We've got square root of 1/3 x squared plus y squared and equals z. Now, by the way, remember, traditionally you would take the positive and the negative square root. The positive square root would be the cone up here. The negative would be the cone down there. So in this case, we just need the positive because it clearly goes up towards positive z, right? So I'm not even going to worry about the plus and minus because clearly it's upward. So I think that should be the lower bound for the cone. So let's see if that's what they got for the answer, and that is. So that's square root of 1/3 x squared plus y squared. Any questions on that? By the way, one more thing. The integrand, let's see, the integrand right here is just 1. Because here's the deal. If you just want to find the volume, in other words, let's find the volume of this region. The volume, in other words, the volume of this cone underneath that that top, then the integrand is just 1. So this just finds the volume. How would you interpret this problem physically if the integrand were not 1? Now listen to me here carefully. This is the best analogy I can think of. When you're integrating over a volume, we know that some things are not constant mass density, right? Now a lot of substances are, right? Like, for instance, you know, the water in my cup here is nearly constant density. If you have like a slab of copper, it's nearly constant density, so on and so forth. But there are some things that are not quite so much constant density. Now, the reason I bring that to your attention is because if the integrand here was, let's say, rho, the density, as a function of x, y, and z, if you integrated that rho over the volume, you'd get the total mass. So even if the density varied east and west, north and south, up and down, that is x, y, and z, still find the total mass over the volume, right? Even if the object was, let's say, shaped like this cone, you know? So who knows? Maybe you're studying like a cone of like some sort of conical pyramid made by an alien civilization. And let's just say they use different densities on different parts of the cone. Well, you still could find the total mass by doing this integration. See what I'm saying? I mean, who knows? Like, I don't know what the exact application is, but there you go. Something like that. Any questions on that?
What I do is I just do the cylindricals and the sphericals with their respective transformation that I have to do.
Right. So, for instance, I mean, I think this is definitely hardest to do in terms of Cartesian, in my opinion, because you have to have a lot of square roots and stuff. But cylindrical, the nice thing is, the imprint here in cylindrical is kind of nice because we're clearly going to go from 0 to 2 pi in terms of theta, and then the radius is just going to go from 0 to 6. So that's how you get the 0 to 2 pi and 0 to 6. But then you have to think about what the z is. Now the z just going to be in terms of, typically you think of z as like the bottom of the cone and then the top of the cone. Well, the top of the cone doesn't change from Cartesian. But then the bottom of the cone is still, where is it here? The bottom of the cone is still 1/3 x squared plus y squared. But the nice thing is, x squared plus y squared equals r squared from cylindrical, right? Because remember, cylindrical is the exact same thing as polar coordinates, except with a z-axis, with a z-axis. X squared plus y squared right there is r squared, but the square root of r squared is just r. So that's why you get r over 3 for the lower bound there. Okay? And remember, the volume element here is r dr d theta for the polar part, and then you got to have a dz as well because it's vertical. So it's r dz dr d theta. Okay? Spherical would be relatively straightforward. Remember, we kind of talked about this. We've got a constant, what's that called? Declination angle, right? So with a constant declination angle, if you want the volume, so everywhere on the cone, the declination angle is the same. Okay, The only reason I'm a little confused is because if this is pi over 3, then I'm thinking it should be 0 to 2 pi over 3. You see what I'm saying? For the declination angle.
Mm-hmm.
And then I do agree 0 to 2 pi for theta. You do have to think about the radius here. You have to go from here to radius out to here.
Mm-hmm.
But the radius is going to change from 0 at the tip all the way out here to the maximum value. But the maximum value is going to actually depend upon possibly phi and theta. Now, it turns out that at any constant value of theta, so if you're looking in this direction, the radius is not going to have any dependence, I think. So you would need to work that out, but I think it can be done without too much difficulty.
So the last thing I'll say, the last word on this video, is that we can find the spherical radius rho as a function of phi, the declination angle, if we use the following equations for spherical coordinates. That is, we know x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. But because we're most interested in the top of the cone, we know the most about z there, and because we want to get the radius, that is the outer radius of this spherical coordinates integration, we want to call this z top, because it's the top of the cone. But that radius is going to be different because when we go up one of the legs of the right triangle along the z-axis, it's going to be shorter, but it's going to be longest along the hypotenuse of the green right triangle we saw earlier. Namely, it's going to be its maximum. So at the top of the cone, the height z is constant. So call that z top equals 6 over square root of 3. But if we take this equation, which relates z to rho and phi, we can solve for rho outer. That is the outermost radius of the spherical coordinates integration. So we say z top equals 6 over square root of 3, and that's equal to rho outer, the largest radius, times cosine of phi. So if we solve that via division, dividing by the cosine of phi, we have 6 over square root of 3 cosine phi. And if you remember on the previous slides we were just looking at, indeed that is the maximum value for the spherical radius. And so this is how we finish out our problem. We've done it in Cartesian coordinates, in cylindrical coordinates, and spherical coordinates. Thank you for watching High Peak Education. Please smash that like button. If you enjoy this content, please subscribe to the channel to grow the channel and share it on your social networks. We look forward to seeing you in the next video.